always dangerous when people applaud before you've spoken anything. So thank you for that kind introduction and setup, I guess. I'm here to tell you how your career is secure for the next 2 decades. It's a pleasure to be here. And so as Guru mentioned, we are tag teaming, and you have a buy one, get one free deal today. And I thought I would kick things off by talking a little bit about the slowing of Moore's law and the opportunities it has for co-design, particularly across the intersection of computer architecture and networking. So let's start off with what the problem statement is. I think for this audience, I'm not going to belabor what Moore's law is. Most of you know that it's an observation by Gordon Moore, the founder of Intel. And he basically postulated that transistor density doubles every generation or so. And since then, Moore's law has become a proxy for an economic law where it's come to encapsulate our expectation that performance per dollar doubles every 24 months or so. So it's a kind of what underpins a lot of the infrastructure advances that we have seen at Google and elsewhere as well. And so if, as you can see from the picture on the right, that's an image from the computer architecture textbook from Hennessy and Patterson. And it shows time on the x-axis and exponential on the y-axis. And you could see that there was a region when Moore's law was fine and alive. And in the last few years, we are starting to see some leveling off of the benefits of Moore's law. And so that's kind of the problem statement that we have in terms of what we are trying to do. But that's just the supply side. And if you focus on the demand side, the picture on the right shows, again, time on the x-axis and exponential on the y-axis. And we have 2 lines there. The line in blue shows the improvement in compute performance measured by SPECint. So that's the advances in computation from Moore's law. But the line in red shows the number of hours of video uploaded per minute on YouTube. And you can see that over time, the red exponential is dramatically higher than the blue exponential. In other words, the demand for computation cycles is far outpacing the supply that we have in terms of improvements in computation performance. Data is way outpacing compute in our world. And that's one lens to look at it. There is a second way to look at this, and again, the picture on the right, time on the x-axis, exponential on the y-axis. And what we are showing here now is the increase in computational demand from machine learning workloads, specifically training from OpenAI. And forget about performance doubling every 24 months. What this shows is that the demand for computation and machine learning doubles every 4 months. And so we have some prolific increase in the kind of demand that we are going to ask of our computers, all at the same time while Moore's law is starting to slow down. But then there's more. And how many people here have heard of Spectre, Meltdown, Foreshadow? A good chunk of the audience. And so for those of you who haven't heard of this, these are basically security vulnerabilities. They are side channel attacks that have recently been in the news, and there's a whole bunch of these kind of classes that we are starting to worry about as well. And the problem with these is when mitigating these security vulnerabilities, you often have to make some pretty sophisticated trade-offs between security and performance. So once again, it's not just decelerating improvement. Sometimes you actually regress in performance because you're going to have to make the trade-off for security as well. And so this combination is really the problem statement that we are facing. So we are starting off with slowing supply from the slowing of Moore's law on one side and exploding demand. And the combination together is the problem statement we want, right? Okay, so that's probably too depressing so early in the morning, but there is good news as well. And the good news is you could look at these challenges, but you could also look at this as an opportunity for us to fundamentally rethink what Moore's law means. And we've really been thinking in terms of, we are now entering a new era of Moore's law. And it's characterized at least by 2 things we are going to talk about today. There are 2 dimensions to think about it. One is we want to be more efficient about how we design systems. And this is efficient in cost, in area, in power, also in time. And we also want to be efficient about how we use our systems. And this is about understanding system balance and making sure we match our workloads and systems very well, look at distributed systems and so on. And one recent theme that undercuts both of these is the use of machine learning to actually amplify how we think of designing systems, and I'll talk about that as well. Okay, so the first one, let's focus on accelerators. And really the trend here with accelerators is we are thinking of custom silicon. We are thinking of taking our hardware and customizing it so that we can make our hardware matched with the workload that we want. So we're going to be area efficient, we're going to be cost efficient, power efficient, and so that's really the intuition behind what we think of with accelerators. And one of the big things with accelerators is the picture there shows what we've been doing at Google. Most of you here have probably heard of the tensor processing unit. It's an accelerator we built for machine learning. And the picture shows the chips that we use, and that's actually the very first TPU generation 1 that we introduced. But we then use these chips to essentially build supercomputers, which is the other picture that you see there. And these supercomputers are really powerful and give you orders of magnitude higher performance per dollar and performance per watt compared to traditional systems. And for this audience, I think you'll be particularly interested. The various colored wires that you see are really the network pipes. It is a large-scale distributed system, and there are some really interesting challenges in terms of how do you feed these really powerful computers, and how do you think about system balance in this context as well. So now I am a system architect, and I can spend a lot of time talking about all the cool stuff with accelerators, how we design accelerators, and so on. But I suspect for this audience, you guys may not be as interested. But so what I thought I would do instead is to step back a little bit, and having kind of worked on accelerators for several years now, talk about what have we been learning, what are the lessons, what are the learnings, what are the insights. And I want to focus on 3 broad observations, and then I'm going to talk about one specific opportunity that I think is very exciting in the networking context. So the first observation I want to make is that even though I described accelerators as custom silicon, as hardware, it's really not a hardware problem. It's fundamentally a hardware-software co-design problem. And so if you see the picture on the right, what that shows is the full system stack. And you can see that hardware is this tiny box with the sliver of green in the bottom. But there's really a whole surrounding ecosystem in terms of thinking about what are the frameworks, what are the ecosystems, what is the software stack, how do you deal with large legacy software that have been built in the pre-accelerator era. How do you think about tools and debugging? And so it's really not just thinking about the hardware, it's thinking about the entire ecosystem as well. And one of the ways I describe it, I paraphrase the popular philosophy quote: if a tree falls in the forest and nobody hears it fall, did it really fall? And so the equivalent analogy in my mind is if an accelerator lands in the fleet and nobody uses it, did it really land? And the point really is we need to think about accelerators as not just hardware. We need to be thinking about it as basically how does it enable the higher levels of software productivity, and what is the ecosystem around that? And if you don't, it's not going to be a very effective accelerator. And then the second part of this picture, which if you see on the left, it talks about, again, the point I made earlier. It's not about single chips. It's about how do you take these chips and build boards? How do you take these boards and build clusters and larger distributed systems? How do you think about problems like virtualization, quality of service, isolation, sharing, making them available on the cloud, and so on? And so really, once again, it's a hardware-software systems co-design problem. The second observation I want to make is that accelerators are fundamentally about capabilities versus efficiencies. And if you forget everything else I said in this talk, I think this is by far one of the most important insights in my mind. And what I mean by that, and it's very non-intuitive, because when you talk about accelerators, most people start off with a pie chart of where do the cycles go, and hey, here is a really big slice of where I spend my cycles and correspondingly my money, and I'm going to invent a super cool hardware accelerator that improves that by a factor of 10, and money is going to pour from the skies, right? And that's fine, and I think that's always a useful thing. But every single accelerator that I'm aware of that has been very successful has been successful not because it was trying to make things faster, but because it created new capabilities that was otherwise not possible. And so the example that I've listed here, if you look at machine learning, when we first started thinking about designing the tensor processing unit at Google, it was not because we had a lot of cycles being spent on machine learning. It was because we had some fundamental capability limits we were hitting. We were looking at our Android phones and we said, hey, if every Android phone on the planet did a few minutes of voice recognition, the machine learning capability that we want to have at Google is going to need us to build a couple of multiple Googles worth of infrastructure, and that's not sustainable. And so really it's important for us to be thinking about, when thinking about accelerators, what are the new capabilities it introduces. And this is particularly true when Amin comes and talks about some of the stuff in networking, is when you make an accelerator for networking that is super fast, it is not as much about just speeding up things, it is as important to think about what are the capabilities that it provides as well. And then the third observation I want to make is to kind of focus on an underemphasized variable in Moore's law, right? So Moore's law is really 3 variables. Its performance doubles for the same cost every 24 months. And there is a third variable, which is time. And what the picture on the right shows is relatively straightforward math. And all it points out is that when you're thinking about exponential curves, if you want to get a 40% improvement over a certain time period, and that's slowing down, you could do that with kind of incremental small benefits at a much more finer granularity. And so you could think about 15% every 6 months as opposed to 40% every 24 months. And the way compounding and the law of exponentials work is it's going to work out pretty good. And the way you're going to be able to kind of do these more incremental, agile, faster innovation is to start thinking fundamentally about how do you create a platform that allows that? How do you think about interfaces, standards, innovation platforms? And so this is something, one of the more exciting recent developments in the context of hardware that I'm particularly excited about. And this is this notion of more collaboration and open source hardware. And everyone here knows, and I think Guru mentioned Kubernetes and so on as well. And everyone knows Google has been at the forefront of a lot of stuff with open source. And in fact, on a yearly basis, we literally have hundreds of thousands of commits that we make to open source repositories. The latest one is in cloud. We have done a bunch of stuff as well. But I think we have an opportunity to kind of provide the same kind of open source ecosystem in the context of hardware as well, where we can make hardware development much faster as well. And so I have a link here to the Google open source blog, where we recently talked about some of the initiatives that Google has been championing, including an effort called the CHIPS Alliance, where we have been very active about thinking about a common ecosystem to have shared IP blocks to be able to kind of think about tools for faster hardware development as well. And being able to democratize and speed up hardware acceleration is, I think, going to be pretty exciting as well. Okay, so those were the 3 broad observations. So I want to take now some time to think about what does it mean in the context of networking. And I want to make one observation here. So far, when I talked about machine learning accelerators and so on, we were talking about really well-defined big workloads that you could have a phenomenal increase in performance per TCO, performance per watt, and so on. But if you look at the dinosaur picture, real workloads tend to have a pretty long tail. And it's not as much about the big head of the dinosaur workloads where we can do stuff. It's also about the long tail. And again, the math is pretty simple. So you have a bunch of infrastructural things that take 90% of your workloads. And if you improve that by 10%, it's the same as getting a 10x improvement in something that takes 10% of your cycles. And so it's important for us to realize that in the new era of Moore's law, accelerators are going to come in different shapes and sizes. They're going to be big, small, coarse grain, fine grain, closely coupled, loosely coupled. And I think this is where we have an opportunity for us to be thinking about accelerators for networking. And to make that point further, the picture on the right again shows a longitudinal study from Google where we looked at where do the cycles go over a period of a year, right? And this was actually very non-intuitive to us when we first saw this. If you think of Google as one big computer running Google class workloads, what the picture shows is 1 out of every 3 cycles or 1 out of every 4 cycles is spent in 6 functions. Right? And these 6 functions are what we call data center tax functions. They are things like memory allocation and so on, but a good majority of them have to do with moving data and networking, things like memory copy, RPCs, protocol buffers. And so really being able to start thinking about this is going to be very critical. And so to dig a little deeper into the intuition behind why this is such an important issue, I want to kind of emphasize that Google workloads are very different from the traditional workloads we are used to. And so the picture again shows 3 vignettes which illustrate that. The picture on the very left shows how a single web search has literally spawns thousands of RPCs touching literally thousands of other servers. So it's kind of very distributed. The picture on the very right shows how on a single machine, we literally have thousands of competing interfering threads, and that's something we need to think about. And then the picture in the middle talks about tail effects. So if you have a large-scale distributed system, even one straggler can kind of, that's your weakest link, and that's going to kind of kill you. And so how do you solve these problems of networking and scale, but in the context of the requirements of large web-scale workloads in terms of real-time latency, reliability, security, efficiency, software productivity, and so on. And so that's really kind of the challenge we have. And so the way to think about this is really what we call the attack of the killer microseconds. And we have a really nice paper in the Communications of the ACM that goes into this problem statement in more detail. But very briefly, it's motivated by two observations, right? Observation one is that we are in the era of microseconds. And if you think about the latency of network speed of light across a data center, that's about microsecond. If you think about accessing an accelerator off of a PCIe bus, that's an order microsecond. How many people here have heard of Intel 3D crosspoint or new memory technologies of that kind? A few people. So, and so these new memory technologies, again, you're talking about whether it's Intel's Optane or whether it is Samsung's ZNAND, they are again order microseconds. And I will submit to you that we are very good at optimizing for milliseconds and nanoseconds. Milliseconds, we have a whole bunch of stuff as kernels, schedulers, so on. Nanoseconds, we have a whole bunch of architectural techniques and so on. But microseconds is this funny beast where we really need to be spending a lot more time thinking about how do we optimize both the hardware and the software stack. And the challenge is that we really need to do that in the context of increased programmer productivity. And so what that picture, the code snippet on the left shows is synchronous versus asynchronous programming. And so how do we do this in the context of more synchronous programming models that are easier on the programmer while still being more efficient and being higher performance and higher productivity? And I think this is where there's a lot of opportunities for hardware-software co-design. There's certainly software techniques to do that, but there's also an opportunity for us to be inventing new kinds of hardware paradigms, hardware queue management, offloads, how do you do bare metal networking? And I think there's some really interesting opportunities there in the space of hardware accelerators. So those were kind of the broad observations I wanted to make on accelerators. I wanted to kind of then finally talk about the other point I made about how we have this new tool in our arsenal around machine learning. And to illustrate this point, I'm going to focus on one more observation in the long tail, and this is around memory. And what that picture shows is Google is a very diverse set of workloads. But one thing that is common across all of these workloads is that if you look at the stall time spent on memory, we spend anywhere from 20 to 40% of our cycles waiting for memory. So for every dollar we spend on our system, I lose 20 to 30 cents because I'm twiddling my thumb waiting for something to come from DRAM. Right? And that's not a good place to be in. And so one of the things that we talked about was to say, hey, can I use machine learning to prefetch? So think of this as basically autocomplete. When you do your search, it kind of anticipates what you're going to be typing. Think of this as autocomplete for memory address patterns, where when I kind of know that I have a sequence, I go ahead and proactively prefetch the remaining things there. So that way the processor has all the data that it wants right where it wants it, and so it doesn't spend that 20 to 30% of the cycles twiddling its thumb. And what is fascinating, and we have an ICML paper that goes into a lot more details, is that this has some pretty fantastic results. And the picture on the left shows how out of the box a simple LSTM machine learning model performs way better than the best championship predictor at that time, and that's pretty exciting. But what is even more exciting is the picture on the right shows how these now machine learning models can actually provide semantic insights into what is happening there. And so this particular picture shows how a machine learning model is able to classify all the memory access patterns into multiple clusters, not just separating them into data structures, but even teasing out how different individual computational patterns operate on these data structures. I think that's pretty cool. And there are two pictures there, and just as a reference, the first picture is basically a traditional spec benchmark, but the picture on the back is a real Google workload. And it's again, I think, very notable to see the richness of the how the machine learning model kind of interprets the real Google workload as well. And this is not just machine learning for prefetching. Is anybody live tweeting here? I thought you guys were all into networking. This is another thing that's a good thing to tweet. I often joke that everything tastes better with a slice of, with a sprinkle of ML sugar on top. And so it's not just in prefetching, but I think in terms of all the things I talked about, designing custom silicon, accelerating the speed at which we do that, thinking about software-defined infrastructure, we have tons and tons of really interesting use cases to think about machine learning, and I think that's a great opportunity for all of us to look at. So I want to close with a couple of last observations. I talked very briefly about custom silicon and how that can counter the end of Moore's law. And actually, the two gentlemen on the top, Dennard and Moore, so they both have laws, Dennard scaling and Moore scaling, and they're both kind of in trouble. And I'm going to leave with the comment that there are a few other laws and rules of thumb that are also worth revisiting. Von Neumann, and von Neumann is very well known for his von Neumann bottleneck and the von Neumann way of designing systems, and I think that is due for a change. Maurice Wilkes, who is very well known for cache hierarchies, and this whole notion of how we think about memory hierarchies, especially in the context of distributed systems, I think that's due for a change. And finally, Gene Amdahl. We all know of Amdahl's law of diminishing returns, but Gene Amdahl also has a second system which is about system balance, and I think rethinking system balance is also very important as well. And so with that, I want to segue to the second part of the talk and introduce Amin and talk about how we can go to the second part, which is how do we use hardware efficiently. And one of the things I think the observations really, and this is particularly true for Google, we've been doing this for several years, several decades now, is to start thinking about the entire data center as a computer. And I think there's a whole bunch of opportunities in terms of thinking about how we think about efficient building blocks that are composed to create the abstraction of software-defined infrastructure and leverage all the benefits that we've seen with software-defined networking there. And so to talk about that, let me introduce my colleague, Amin Vahdat. Thank you.
Thank you very much, Partha. It's going to be tough to follow Partha in that this is always a very, very compelling story in terms of what's happening in computing. I'll start with maybe a little bit of a side story. It's a bit of a disconcerting day for me today because to my simultaneous honor and horror, my two daughters are starting to watch my talks on YouTube. They told me recently, you know, you're a pretty good speaker, Dad, but why do you always wear blue shirts? Which is true. So today, I'm taking a bold step. I'm wearing a shade of red. Hopefully, it doesn't screw me up too much. So let's see. Software-defined infrastructure. So Partha and I have the privilege of working together with Partha closely, and I think that really we talk a lot about programmability in the network. But I think that the models that I like to think we've been going after for the past decade or so really are more general, and I think there's huge opportunity going up and down the stack. So what does all the things that Partha said, in other words, computing is going to be changing radically over the coming decade. All the things that we've taken for granted over the past 30, 40, 50 perhaps years are going to be going out the window. In other words, this isn't something that, hey, Partha's telling you is going to start happening 5 years from now. It started happening 10, 15 years ago. And I think that we're really hitting the inflection points about we need massive change. What does this massive change look like? Partha really nicely put together the shift from milliseconds to microseconds. And I think that this is really going to be a big change for us because our software for let's say at least 20 years, has been at a place where if we think about what it takes to get from one server to another across our networks, it's about a millisecond. So when I was an undergrad, which is also to my horror, an increasing number of years ago, an RPC took about a millisecond. If you ask most engineers, even at companies like Google today, how much should you budget for an RPC across your data center network today, 25 years later, It's about a millisecond. And so we've built just a ton of assumptions into our software stacks, into our hardware, about what's the baseline latency across our infrastructure. At the same time, there's been, Partha showed all the graphs, factors of 10,000 plus in the improvement of performance on the CPU and on the storage side. So now we've got this network that's dawdling along at a millisecond with these processors that are burning, right? And they're burning waiting for data, because all of the data out there is network data. For better or for worse, right? You can't get at all the data that you need for edge computing, for machine learning and everything else without going across the network. So this is going to have to change. And at Google, we're thinking of this in terms of from milliseconds to microseconds, but from clusters to cliques. So fundamentally, we're thinking about smaller units of compute. We've been on record for our data centers, our large clusters, tens of thousands of servers, uniform access across these tens of thousands of servers. This has worked great in previous eras, previous epochs, as I'll be talking about shortly, of computing when storage was disk-based. Right? If you're talking about accessing data that has to hit 10 millisecond minimum, right, to have the mechanical arm get to the right sector, hey, millisecond network isn't so bad. It's just 10% overhead. And if you can have the power of having all the disks in the data center at your fingertips, awesome. Like the network isn't any impediment to it whatsoever. Now we're going to be living in a world, we are living in a world, where storage is increasingly in the 10 to 100 microsecond range. And as Partha pointed out, we're going to be increasingly moving to stable storage with emerging technologies that are in the 1 microsecond range. Now, all of a sudden, that millisecond network that's been okay, that hasn't been an issue for 20, 25, 30 years, is no longer going to be okay. There's some fundamental physics involved. We can't necessarily get to 10,000, 20,000, 30,000 plus servers with uniform bandwidth and really low latency. But think in terms of, well, can we get to 100,000 cores? What would that mean? 1,000 servers, 2,000 servers, 3,000 servers, a smaller number. Can you build that in a small diameter, where to each server you provision non-blocking bandwidth, 10 times or higher what you would do today, where you would deliver radically different latency. So in other words, I think going from this millisecond scale to, I'm not sure we'll get to a microsecond in the very short term, but it is achievable to get to 10 microseconds in the very short term. Like that is eminently possible. We have a huge amount of work to do there. But again, now we're thinking in terms of server racks, however it takes to get to approximately 1,000 servers, where can you start thinking about them as a fungible pool of compute, a fungible pool of flash, a fungible pool of NVRAM. DRAM will be tougher. I have it on the slide because I think it's interesting to think about, but DRAM is fundamentally in the 50 to 60 nanosecond, 70 nanosecond range in terms of access latency. Huge amounts of bandwidth. Networks as we currently think of them today aren't going to get there. Like there's no way that you're going to make remote DRAM look like it's local for a variety of reasons. But still, leveraging that capacity at the scale of 1,000, 2,000, 3,000 servers, I think is where we need to get to in terms of what distributed computing looks like moving forward. So let's look at a bit of history. And I think it's somewhat easy for me to say we need a lot more bandwidth, we need a lot lower latency, but I think it's more compelling to look at it as a logical combination of history. In other words, this is where we've wound up because it's been inevitable that we get to this point. So bear with me. There's a lot going on here, a lot of history here. But I roughly split things up into 5 epochs of distributed computing. The first epoch started roughly around the time of the birth of the internet. So think of it as early to mid-70s. This is when distributed computing was about FTP, email, and telnet. We had low bandwidth, high latency networks. Right? It was about 56 kilobit per second leased lines. By the end of this epoch, we had T1 lines coming along, right? Imagine a megabit and a half per second of bandwidth, right? 1.5 million bits per second. I remember that and remember how stunning that was to think about. There was rare pairwise interactions between expensive computers, with most of these interactions really human mediated, right? It was about email, it was about telnet, a human being typing at another computer, let's say, maybe having to upload files, etc. Early 80s, maybe a decade later, 1984 was actually when the remote procedure call was invented. This is what shepherded the era of client-server computing. Right? This is when local area networks became commonplace, 10 megabits per second, right? Maybe a factor of 10 faster than the last epoch. And now we were thinking in terms of this client-server computing model and shared resources between multiple computers. This is when Sun's XDR came along, right? And we started thinking about NFS. Right? I now have some resources on another computer. My storage is on another computer, and I'm not running FTP to transfer things back and forth. I'm actually accessing my files over there. That was a big deal. Epoch 3, perhaps another decade or so later, early, mid-90s, HTTP came along. 3-tier services came along. And massively parallel processors came along. Now we were talking about an era of 100 megabit per second, even gigabit per second networks. The applications no longer fit on one server, right? So when you accessed a web service, it was commonplace to think about going to a front-end web server that would then communicate synchronously along the path of a single request from a person with an application server, which would then talk to a database server behind it. Right? So applications are getting increasingly complex. They're coordinating with one another on sort of human interaction timescales on gigabit per second networks. Epoch 4, I'll argue that's where we are right now, perhaps at the tail end of Epoch 4. And this is also referencing back to Partha's presentation, where Moore's law hit its first wall. We were still doubling the number of transistors per second when this fourth epoch, around the early 2000s, took place, but single-threaded performance essentially stopped improving. And we've been actually in this state for about 15 years now. 10 gigabit per second networks emerged in this time period. We moved from disk to flash. We're still actually in the process of moving from disk to flash fully, but certainly at the tail end of that. And we developed some software layers to manage large resource pools. At Google, this would be things like GFS, the Google File System, or MapReduce. Now we could imagine, certainly for disk-based data, leveraging hundreds, thousands, perhaps even tens of thousands of servers to provide a uniform storage pool, to provide the ability to simultaneously do data processing on huge amounts of data, terabytes and increasingly petabytes of data synchronously. And I would argue that we are now entering Epoch 5 of distributed computing. And this is where, as Partha pointed out, we are hitting the second wall in Moore's law. We now are essentially at a place where the performance normalized the cost, in any case, of a single socket has plateaued. And this is a big deal. What this means is that if we're going to continue delivering the impact as the extended computing community, and I'm now not just talking about networking, I'm talking about the computing community. If we're going to continue delivering that kind of impact where we can go after ever bigger problems for ever lower cost, we have to shift what we do. And so this has led to accelerators and machine learning and a lot of the great things that Partha discussed again. So now we need to say, if we're going to continue delivering performance cost improvements, we have to look to TPUs, GPUs, larger scale, more tightly coupled distributed systems. This is the era of 200 gigabit per second networks. This is the era where we're talking about openly our terabit networks that are coming, interconnecting these servers to one another. Okay, so what does this fifth epoch, the one that we're entering in now, we're still at the tail end of the fourth epoch, but what does this fifth epoch mean? I believe that future performance TCO benefits, TCO total cost of ownership, is going to come from shifting how we do computing, right? And so think in terms of where we were before. You write your code, you wait 18 months, new server comes along, your existing unmodified code gets a lot faster. I mean, how awesome was that? Right? Unfortunately, I think those days are over. Right? We can't write our code the same way and expect the new hardware to come along and make the inefficiencies go away. So this is going to be painful, right? This fifth epoch is going to be among the most painful out there because we can't do business as usual. And we have lived with loosely coupled distributed computing with ever-improving per-server capacity as the rule for scaling for decades. And that's going to have to stop. And again, I'm going to argue it's inevitable that it must stop. Okay? And that means the boundaries have to continue to blur between compute, network, and storage. But these storage elements, these accelerators, are microsecond scale. they're no longer millisecond scale. And that means that our software stacks and our hardware to coordinate it all is going to have to change with it. So in the time when you could wait 18 months and your code would get twice as fast, this didn't come for free for the entire community. A lot of people had to work hard to say underneath this abstraction of machine code, we're going to do a huge amount of optimization, right? Microarchitectural optimizations, hardware optimizations. Now we're going to have to move to system-level macroarchitectural improvements, right? We have to, unfortunately, pop up to get the next level of improvement. So this means co-design of software, hardware, and accelerators, also as Partha referred to. And this means we're going to have to do something scary for the whole community. We're going to have to move toward more tightly coupled distributed systems that are simultaneously easy to program. So I think that if you just do back-of-the-envelope calculations, what you can see is that for whatever large-scale programming problems we're solving today, if you pencil it out and said, if I could have all my 100 servers working on this one problem, or my 1,000 servers working on this problem, working in unison, how much faster could the job go? And I think you'll find that the answer will commonly be at least a factor of 100 faster. Not a factor of 2, not a factor of 3, but if you think in terms of what's the raw performance of the storage, the accelerators, and the compute, that 100-server distributed system should be able to go 100 times faster. And this is for well-tuned, well-implemented systems. This is not a hack. This is not something somebody threw together in a week. This is for production-scale systems that have stood the test of time. There's a factor of 100 on the table. How are we going to get that factor of 100 back? How are we going to get, 7 doublings of Moore's Law to keep us moving forward? Okay, so where are we right this moment, and where do we need to go? On a server, we have a general purpose computer with plateauing perf per TCO. It's connected via very high speed, very low latency memory bus. We talked about 65 nanoseconds, 50 nanoseconds, to local DRAM. Unfortunately, DRAM is getting increasingly expensive. I don't know the current trends right at this moment, but the two are in a race in terms of which costs more in the servers today. It's not only very expensive, it's hard to size. Right? You have to deploy it in sort of increments of a factor of 2. Right? Is it 128 gigabytes or 256 gigabytes that you need? Well, if you need 129 gigabytes, you're paying for 256 gigabytes. Right? So how do you size it, and how much do you pay for it? How much do you strand if you can't size it perfectly? We have this PCI bus that's been living with us for 30 years or so. Its latency is comparatively enormous. So we go from 50 nanoseconds to, let's say, a microsecond for an amazing PCI implementation, and likely higher than that in practice. So it's comparatively much higher latency, and it's rather slow to evolve, even on the bandwidth side. And this is where all the other peripherals start to live. Flash, right? Finally fast, but it's not nearly big enough. Right? You can't put enough flash into a single server to solve the kinds of problems that we need to solve today. Accelerators, whatever kind of accelerator is your favorite, a TPU, a GPU, many others that are emerging. But these are very expensive. Right? Because they live on the other side of a PCI bus, they have to work in batch mode. And you have to amortize their cost over having huge amounts of capacity. Right? In other words, they go amazingly fast, but you have to keep them fed with large amounts of data. And it has to be streaming at it really, really fast to keep these things occupied. So now think of it from a programming model perspective. Partha again showed a really great graph that said malloc is really expensive. Compress is really expensive. Now, we could build hardware to solve those problems. But can we really send 200 gigabits per second, 200 gigabytes per second of mallocs at an accelerator across the PCI bus and have it mean anything? The answer is no. Actually, that doesn't make any sense. But then what's the system design where it does make sense? How would we make these things go much, much faster? And then finally, the NIC, the interface to the network. Right? Unfortunately, very loose coupling with application communication primitives or thread scheduling. So the vast majority of very, very advanced developers think about the network in terms of a remote procedure call. They don't know about IP. They don't know about Ethernet. They don't know about TCP. They probably know a little bit about it. But what they think about when they think about the network is remote procedure call. And that abstraction is very high level. and the NIC is thinking about putting IP packets on the wire. Right? How do you schedule an RPC handler when the packet arrives? Which RPC handler do you schedule? What's the mapping from the applications view of the network to the physical view? Right now, we don't have a way to connect the dots. Okay, so this is the local view. We build large-scale systems. We solve the problems that we do by coupling these together. But there really is a hard boundary. People think hard and long about ever leaving the safe confines of a single server. Right? Do I really want to make that procedure call? Right? One of the things that I'm very upset about, it's the right thing to do, but I'm very upset about it. When our most advanced development teams for our services want to add a remote procedure call to their system, they think twice, they think 3 times, and then they ask for approval about whether or not they actually want to brave what happens when they leave the server. Right? Huge amounts of data, huge amounts of processing power, huge accelerator capability outside the server, but really scary out there. Right? How do we make it a lot less scary for people to think about leveraging the network? Right? Okay, so to summarize, servers are expensive and underutilized. This trend is not changing, it's getting worse. We are, however, we are fighting the perf per TCO trends. We're doing it by building bigger and bigger servers. And it's probably the right thing to do. But what that means is that they're getting ever more expensive. And that means that we have to work harder and harder to keep them highly utilized. So these costs are increasing with specialization, with scale, and with storage, right? Put more accelerators into a server, put more flash storage into a server. Again, all the right things to do, but also dangerous from the cost side. Now we're going to have these bigger servers, which means we have to do more multiplexing. We have to put more applications on the same server. But this breaks down isolation and predictability, right? We talk about getting to microsecond scale, but and Partha showed you some really nice visualizations of what happens among the thousands of threads that are running simultaneously on a server. How do you deliver microsecond granularity communication primitives and coordination primitives to these services when you've got thousands of threads with no good mapping to network communication primitives, by the way, contending for the CPU and the kernel, et cetera? Right? So isolation breaks down. And as we've already discussed, these accelerators are today hard to program because of the asynchrony and the batch model, right? You have to feed a huge amount of data to keep them moving. How do we break down the barriers between these elements such that if you want to leverage an accelerator, you don't have to think about it really, really, really hard, right? And hand tune your code perfectly to leverage the acceleration capabilities. So what are the hardware and software capabilities to manage data flow and these asynchronous events, right? If we're talking about communicating at microsecond granularity, you are going to have asynchrony, which is going to be very, very hard to program about. How do we think about making it easy for the field to advance? I'm inspired by the famous quote from Hennessy and Patterson, for better or worse, benchmarks shape a field. I think one of the reasons we've had Moore's Law is because we've had fantastic benchmarks that inform the community. Right? You run this benchmark, you make it X% faster, you have done some good. You could argue about the flaws of the benchmarks, and there have been many, but they've pushed the field forward tremendously. I would say that we have not done a good job of building the equivalent benchmarks for the distributed computing, the networking communities. How do we know when we're making things better? We talk about going from 40 gigabits to 100 gigabits to 200 gigabits per second. And of course, these are stunning achievements, soon 400 gigabits and beyond. But what does this mean for the application? Right? And actually, I would say we don't know. And almost certainly going from 100 gigabits to 200 gigabits per second doesn't mean we double the application's performance. Right. So what is the right hardware and software support for macro architectural optimization? How do we get back this factor of 100 between what the distributed system should be doing and what the distributed system is doing? I don't have an answer to this question, but I'm very interested in trying to figure out the answer to this question. So let's go back to the 5 epochs, right? And now we're going to give them some names, right? The internet birth, the client server, to the era of web in Epoch 3 and the I/O wall, to max single-threaded performance with massive scale-out, right? This is the epoch that we're in. This is planetary web services. And now maybe the rise of Epoch 5, max general compute, emergence of accelerators, and the tail at scale getting to 10 microsecond latencies. I would say that the programming models to leverage the capabilities of the underlying hardware are key here. So let's look at what it means to manage concurrency. Right? Concurrency is the bane, perhaps the #1 bane for all developers. And it was kind of beautiful in Epoch 1. You didn't have to worry about concurrency, essentially. Things weren't happening simultaneously, and if they were happening so slowly that you could treat them as being sequential. In Epoch 2 with client-server, this is when event-driven concurrency came along, right? And maybe many of you, I don't know, certainly me, wrote a lot of code around select loops. Right? What events came in, which socket is active, how do I hand that socket off to a particular function that's going to process the data on that socket for a while, finish its job, and then go back to the event loop. This was kind of a pain, but it was kind of fun too. Right? So I would say that if I could handle it, most people could handle this event-driven concurrency model. Then came the early 90s, right? We hit this max single-thread performance, and now we had to have processors that had multiple threads. And this meant that concurrency had to move to multi-threading for latency hiding. Right? You couldn't live with the plain event-driven model anymore. And this became hard. Right? Dealing with multiple threads that are reading and writing shared data structures simultaneously is really hard. And it's deceptively hard. In other words, smart people can very easily convince themselves that they know what they're doing and that they can manage the complexity associated with the concurrency here. And probably with a lot of work and big teams, you could. Now in Epoch 4, you had to push further on multi-threading for performance. Right? And the problems became harder. Now, though, looking at Epoch 5, this tail at scale epoch, this 10 microsecond epoch, you're now no longer thinking about dealing with your concurrency on a single server. I'll argue that you have to coordinate across multiple servers simultaneously. Right? No longer are you thinking about the predictability of 2, 4, 8 threads on one server, 20 threads, but now you're talking about threads that are simultaneously running on different servers across a network. So looking at epochs 3 and 4, what I'd say is very few can get this right. It takes very disciplined programmers with maybe a decade of experience to really get multi-threading right. The correct approach depends on the workload and the system balance. So what I want to say here is that, for example, for web search, every time the hardware changes, every time the number of nodes in your distributed system changes, every time the flash technology changes, or the disk technology changes, or the network performance changes, there is an incredibly talented team that is going to retune the behavior of the distributed system, thinking about the concurrency and eking out the last ounce of performance. This doesn't scale to every application. Right? We can do this for a few applications at Google. We can't do it for all the applications at Google. Now in Epoch 5, I'll argue that essentially it's going to be impossible for any human being to manage the concurrency across multiple threads, across multiple servers. And I'm sure that for a PhD dissertation once, someone can do it. But it's not going to scale, it's not going to generalize. So what do we do here? And what I'll argue is we will need the equivalent of an operating system, not a single server operating system, to manage distributed runtime state. We're going to need to move to a world where we have declarative specifications of our distributed computation and the ability to map that declarative specification to individual servers and individual threads on those servers, trying to have humans orchestrate the low-level microsecond granularity communication among servers on a changing pool, heterogeneous changing pool of servers, flash, accelerators, and networks. It's impossible. I'll say it that strongly, it's impossible. So that means that we're going to have to enable the developers to specify their business logic, right? That's now the new abstraction. And we optimize underneath that spec of the business logic, right? What is your distributed computation trying to do? Now, how do we map that to available compute, storage, networking, and accelerators in real time, right? Perhaps in the face of multi-tenancy. All right, so let's see how this plays out. In the fourth epoch of computing, here is a common, let's say, very common, very powerful design pattern for how we build large-scale distributed computation. Think of it in terms of a query comes in. We have a bunch of data that we have to consult in real time, milliseconds, to answer a human-based query. Maybe it's web search as an example. No one server has the capacity to handle the internet index. Right? No one server can say, you gave me this query for travel in London, whatever the query is for, and I'm going to be able to give you the answer. So we have to partition the state across hundreds or thousands of servers. The way that things work right now is that essentially we are going to take that query, it's a bit more, much more complicated than this, but this is not far from reality. We're going to take that query and we're going to simultaneously broadcast it to 1,000 servers. Each one of those 1,000 servers is going to have a partition, let's say 1/1000th of the internet. It will look at its partition, it will come up with the best answer it has. It will then send its best answer back up to the coordinator, which will then compare the 1,000 best answers, score them, and come up with one result. And again, it winds up being a bit more complicated than this in practice, but this is the design pattern. Right? You take your data set, you partition it across however number of servers you need to partition it across. Of course, there's the complications of replication for fault tolerance, et cetera, but that's the model. You send small queries to each of your workers. They look at huge amounts of data. They reduce that huge amount of data to a rather small amount of data and send it back to a coordinator, which will then do a join. Okay. Lots of benefits. It's a very powerful design pattern. It generalizes, but it comes with many cons that all eat into the possible performance of your distributed system. You can't branch. You get one pass over your data, maybe two, right, if you're going to go back and ask them a second time. It requires substantial data reduction to work. Right? There's enormous amounts of data on each one of these servers. You're only sending them small queries and getting small subsets of the data back. You have to statically partition your data set. Right? Again, human beings are going to look at with domain-specific expertise and say, here's my data set, how do I partition it best among my servers? If the data set changes, there's no way that someone is going to come in and repartition. We're going to make our best approximation. Data is going to be pre-replicated anywhere it might be needed. And remember, we look at every remote procedure call with skepticism. So given a choice between making a remote procedure call and replicating the data locally so that we don't have to make a remote procedure call, again, I'm exaggerating, we're going to look at the data locally and replicate it and pay for that replication rather than make a remote procedure call. Okay, and so it does require this very careful per application tuning, or just saying, I'm not going to tune it for this application. It might be a factor of 2, a factor of 10, or a factor of 20 off for this particular application, but that's okay because I can't afford the cost of tuning it, the human cost of tuning it, and the human time of tuning it. So one might say, okay, how do I move from distributed systems to distributed runtimes? And I won't go through the details here, but you might imagine that an alternative view here would be, okay, I have my specification, my declarative system specification, right, that I write as the developer, and there is a view of runtime state. And then there's a distributed runtime that says, how do I move code to data and data to code? How do I flexibly place a query so that it can go to the right partition of the data, and perhaps even consider repartitioning the data, moving data around underneath the hoods as necessary, as the underlying data set or as the underlying query patterns shift. Now, there's a huge amount of complexity here, but the point here is that we can perhaps get this right once in the equivalent of a compiler and in the equivalent of an operating system. We can imagine putting one team on this, or 10 teams, but we can't imagine asking every application developer in the world to think in terms of this complexity. Okay, so to get, and by the way, these epochs last a long time. So this is not something that we're going to be able to solve in a year or 2 years or 3 years. So maybe this is to Guru's points in terms of job security. I think that we've got more than 10 or 20 years of job security, I'm pretty sure. But getting at some of these things is going to be hard, and it's going to take a long time. To keep driving this future performance TCO benefits, I think we have to rethink the basic architectures for interactive serving systems. And all sorts of other things. Basically, do we do function shipping versus data shipping? What are the granularity of load balancing decisions that we make across our servers? And we're going to have to account for tightly coupled scheduling of these resources across multiple domains. Okay. So this is scary. Right? again, since we're talking a bit about history, MPPs failed, SMPs failed, distributed shared memory failed. The stuff we're talking about is really complicated. I'm personally scared by these items. I was around for, I think, all of these failures. The counters are, I don't know what choice we have. In other words, we can go after this next wave, or we'll be stuck with not being able to solve ever bigger problems. Okay? We have made huge progress since the late 80s, early 90s, mid 90s, when some of these failures took place. We now know what it means to do multi-threaded programming. Right? In the late 80s and early 90s, we actually didn't know what it meant to do multi-threaded programming. We've come up with, we've had to live with NUMA, non-uniform memory access. We are developing chiplets. Bonus points to the first person who can tell me what this picture on the right is after the talk. Okay, so tight coupling requires great expectations. If we're going to bring these nodes together, we're going to have a lot of work to do in terms of not just driving more bandwidth in the best case and less latency, but in general. So what do we need from a future platform? I think on the networking side, I've mentioned things like this before. We wouldn't have the internet today if it weren't for some of our baseline, deeply seated tenets around best effort and soft state. But think about it. When we say, what is the network service model? We say, well, if you give us a packet to send, we're going to do our best to get it there, but we don't know when, we don't know if. Right? You keep track of it, and if it doesn't get there, you tell us and try sending it again. So whoever negotiated that contract, I think, was a genius, because this is a pretty easy contract to deliver on, but it doesn't actually enable the kinds of distributed systems that we have to be building moving forward. So imagine if the memory industry said, 1/1000th of your DRAM accesses will take a millisecond. Not 100, sorry, that should say typo, not 100 nanoseconds. That just wouldn't fly. From a developer's perspective, imagine that you're accessing DRAM, and 0.1% of the time, you're going to have a slowdown of a factor of 100,000. Your code wouldn't work. What if we said 0.1% to 1% of I/O or accelerated completions take a millisecond to return? Again, that's not going to work from a developer perspective. So in other words, the wide variability has to be reduced dramatically. We're going to need latency predictability, and we're going to need stability. And this is all going to have to be based on consistent, what I would argue, meaningful benchmarks that we can use to drive improvements. Okay, so I think in the interest of time, I've already made this point in terms of developers think about remote procedure call. They don't care about IP, TCP, or Ethernet. So let me close. I believe, and I think I speak on behalf of my colleague Partha as well, we believe that future computing platforms critically require more efficient, more reliable, and more flexible networks. I think there's just a huge amount of exciting, scary opportunities. We need efficient silicon. We need designs that scale to their warehouse scale computer. Yes, we need software-defined systems, not just software-defined networking. In the end, right, we're talking about disaggregation of storage, of compute, of accelerators. And that is all going to be tied together by the software framework that pulls it all together. Lots of opportunities in terms of in-network programming, right? What are the primitives for coordination, whether it's in terms of barrier synchronization, consensus, leader election, or otherwise? Can you imagine leveraging this kind of capability in the network? Actually, many in the research community have, and have done some really nice work here. Could we perhaps bring some of these things to the forefront? Data centers will increasingly be data-centric. Right? Again, can you harness the entire scale of the data center to be housing warehouses of data that can be computed upon with a runtime that manages it all? And I think to get there, actually, it's going to take huge amounts of co-design of both the network and the computer architecture to get there. Right? And what I hope I've argued is that doing so is not just a nice-to-have, it's a must-have. Right? Otherwise, actually, the whole computing community is going to hit a wall, not just Moore's Law. Okay, and with that, maybe I'll invite Partha to come up and we can answer any questions.
Okay, wow.
talk.
I don't know whether I should be excited or should be depressed, but maybe some combination. But
Both.
okay.
All right, thank you, Guru. Both of you guys, very illuminating, provocative, stimulating talk. Thank you. My question for Amin, how is this new computer architecture, new IT platform going to evolve? Is there going to be some new industry consortiums? It's very doubtful that the hyperscale cloud companies are going to get together and cooperate on this. Is each one going to do their own evolutionary path for this new computing epoch and model that you've highlighted today? Thank you.
Yeah, great question. I'll also let Partha comment. I think it's a real danger in terms of having each individual compute platform provider develop its own. I think a benefit that we had was over the past 30 years of the commonality where you could innovate underneath a common abstraction. I hope that something like that happens moving forward. In other words, presentations like this are about really reaching out to the community. I don't have an answer in terms of specifically what this new computing platform is going to look like. But I do know that it's not going to work if we say, here's how you write really great code on cloud platform X, and here's how you do it on cloud platform Y, and here's how you do it on cloud platform Z. That's the fastest way to actually. So will we need some standards and some agreements on benchmarks and interfaces? I believe yes. I'll let Partha speak more on this.
No, I think the answer is yes. I don't know if you're going to need a new consortium or existing consortiums need to evolve. So I will give you the example of CXL. So CXL is a new standard for communication, and we have Intel, AMD, and ARM announced yesterday that they're doing things as well. So we are getting some traction there. I'll point to Open Compute and Open Power. So there's a bunch of these areas which are already thinking about it, and so we just need to kind of change the narrative to Epoch 5, as Amin pointed out, and start thinking about what do we want to use these systems for. And this is a great venue as well. And so I'll throw the challenge back at this community to say, what should we be doing here to kind of think about some of the ecosystem we want to build as well.
So I want to, there's a possibility that some of the people may be thinking, oh, this is the problem, and the way the question was articulated can also suggest, oh, this is the problem of these three companies, Google, Amazon, Microsoft, maybe Facebook. I don't need to worry about because I don't do this kind of computing anyway. So what would you say that, why is this relevant to a larger ecosystem or anybody who does computing and networking?
Yeah, great question. I would say that we all, of course, have this is a problem that's bigger than any one or any three companies. And I think that we really are talking about fundamental shifts in terms of how computing is done. There's no cornering the market on great ideas. For example, I think a lot of the questions that Partha and I asked throughout the talk, at least I won't say neither one of us know the answers, but I don't know the answers to them. So, and I spend a fair amount of time thinking about them. I think that suggests that we're going to need a lot of participation, and in particular, the network, showing my bias. I also want to enable the community to think in terms of, it's not just about WAN, it's not just about edge, it's not just about data center, it's about coordinating with storage and compute deeply to enable some of these different use cases.
So if you don't mind, I want to ask a follow-up question.
Sure.
So how many of the people on Google Cloud, for example, ordinary users that come on Google Cloud and run their apps, run into the same kind of performance issues that Google runs into for the specific workload that you guys are running, the search or machine learning for things. So if there are ordinary users that come on Google Cloud, they are also running into same performance thing, then the problem is much more widely appealing in some sense. I mean, that's one way to think about it.
Yes, and I'd say close to 100% today are hitting it on any cloud, not just Google Cloud, because we've hit this, and I think Partha's data showed it very compellingly. We've hit the perf TCO wall. So in other words, even if you're running on a few servers, or even if you're accessing storage or whatnot, you're not getting the improvements that today, every user or consumer of compute isn't riding the waves of economics that they've been accustomed to over the past 30 years. Just sort of period, full stop.
Oh, okay.
Not just Google, and not just Amazon, not just Microsoft.
And I'll also add that you should really think of Google the apps as kind of a leading indicator of what everybody's going to do. If you look at web search from 15 years back, and if I look at cloud customers, they are writing sophisticated applications that are more powerful than web search from 10 years back. And so I look at TensorFlow, and I look at some of the customers using TensorFlow on the cloud, and they are pretty sophisticated stuff, and they are going to start worrying about some of these issues as well. So it will, depending on how aggressive the applications and customers get, it's going to get very useful.
Excellent. I think that is, yeah, exactly. Okay, go ahead.
Where do you think we're going with the future of routing, switching protocols as we really get to a programmable network? And are these going to become quaint antiques as we sort of move to a world of clicks where we try to give programmers an RPC view of the world and liquefy the underlying network?
So sorry, I missed, the question was where we're going with which aspect of this?
Routing, switching protocols versus really just building a programmable network.
Yeah, it's a great question. I think that this presentation, this co-presentation focused on what's happening in one location in the network. I would say that switching protocols are actually going to be key if we peel one more layer of the onion. In other words, if you're talking about delivering predictable microsecond latency, that essentially says no queuing. And it says and so if we're delivering predictability, that there's going to be some of these scary things like no queuing and no loss. Now, is that a guarantee? No. But can that be happening in the common case for 1% or 0.1% of the packets? No. So what would be the switching protocols that can get us there? I actually think that the ideas and even some of the realizations are out there. They're probably years away from large-scale realization. Routing, if you're talking about standard ISIS, OSPF, BGP style protocols, of course they're going to be playing a role here, maybe less critical in terms of this will be the gateway to how you talk to other cliques or other clusters, which of course is critical for its own reasons.
Okay, I think we are running out of time also, so thank you, Amin and Partha, really appreciate it. And again,